Welcome back to I'm Finally Reading My Brother's Book. In today's episode, Gavin and I dive into some of the strangest, most mind-bending parts of physics. We imagine ourselves inside a wave and then ask, where did that wave come from? We ask, what exactly is space? Is there something in the void? We'll talk about the music of the Big Bang and why imaginary numbers are essential for making sense of the quantum world, especially when particles are doing 720s instead of 360s. This chapter solidifies our foundation for understanding our universe, the observed and the unobserved parts. We even get to sample a new song that Gavin wrote. So let's dive in. Quarks!
Hello.
Just kidding. We're actually not going to talk about quarks very much, I don't think.
No, we're not going to talk about quarks at all today.
Yeah.
That's a funny way to start.
No, so this chapter in Gavin Vassen's book is called Narrative something. I don't remember. Let's see. Narrative space. We're talking about space.
It's
We're getting
chapter
back
3.
to basics.
We're on chapter 3.
I love space.
Narrative space is basics for you? Yeah.
Yeah, so well, space, the basics, just talk about space.
Got it.
I will say, of the book chapters so far, of all 3 that I've read, this was the most confusing, and I feel like it's just going to keep getting progressively more like, I'll post a picture, but I'll just show Gavin right now. This was the face I made when I got to spinners, which we'll get to. I'll show you my face.
You took a picture of yourself?
Okay. I'll post that in the podcast notes if I can or something. It's just
maybe that's the episode card.
Cover art, yeah. Well, but first, before we get to spinners, we're going to talk first about what if you're inside of a wave function?
Yeah.
What's that like?
Yeah. Well, let me back up and address what you said. Okay, so yes, it's and the book is complicated. There are a lot of ideas. And I think part of it is just me not being a great writer. If I had taken more time to be a little bit more gentle with the reader, but I was in grad school and there was a lot of flexing, and this is what all my friends were doing with their intellectual flexing. This is what you do. So I do sort of quickly jump in and out of concepts that I could take more time to build up to.
It was
but
funny.
That's why we're doing the podcast. So
yeah, I remember when you wrote the book, you told me you wanted it to be a coffee table book. Coffee table book for really, really smart physicists only.
No, I mean, I really wanted to interact with the field. And I did. I think I am making some contributions, even if they're not formal here. But anyway, to make it more accessible to people who are thinking about picking up the book, who've actually just only listened to the podcast so far, there's only 4 concepts to understand, and we're going to talk about them throughout. But the first is we're going to talk about the probability wave that we established in chapter 2, but instead of thinking about it from the outside in, we're going to try to think about it from the inside out, which is a really fun kind of thought experiment. Then we're going to talk about space, in an Einstein way,
just
a relativistic way. Yeah, that's a good question. And then we're going to talk about horizons, temporal and spatial horizons, which we've already talked a lot about in chapter 1.
Yeah, apparently, when your temporal horizon just freezes.
Yeah, we'll get into that. And then the fourth thing is spinners, which is a more complicated way of saying we're going to talk about imaginary numbers and imaginary stuff and how that's useful in math. So it's really not that hard. If you've ever thought about imaginary numbers, you've already grappled with this idea.
I have not.
Okay.
So we will do it together. I knew they existed, but I thought it was more just for giggles. I don't know.
It's the same as the concept of 0 or a negative number. It's just a math trick. That's a placeholder for a certain kind of thing.
But I can visualize 0. It's like space.
Can you though? Okay. Let's do it. So at the beginning of the chapter, you say, okay, imagine you were a piece of water, a water molecule, right, and you're in the ocean. And you're just minding your own business, and you're kind of getting pushed around by all the neighbor water molecules, but you're used to it by now, so that's pretty normal. And then all of a sudden, everybody stops pushing, and they all kind of move in one direction and go up and then down, and then you're back to the same spot. You didn't even go anywhere. But what just happened?
Right.
What was that thing? And how can I define that thing? And the same way that we said, tornadoes are this weird, ineffable quality about like the way that things move and like the history of the probabilities of the blah, blah, blah. It's a similar thing, right? But now the way to think about it is like, if I wanted to understand what happened, I'd have to like look and say, well, where did it come from? Which
Mm.
could be a very much more difficult process than the one where I was like in an airplane chasing the hurricane or the whatever and saying like, okay, I can write down where it's going because I have some initial observations and conditions and I've like kind of understood it, even though it's not perfect, but I'm still like this entirely probabilistic object is sort of acting like a little like a marble
Mhm.
rolling down a path and I can just, model it or think about it that way. Now you have to do something more tricky where you have to say, what are all the things that could have caused that to happen? And what is the imaginary space of things that could have happened to make that wave pass through this little neck of the woods? And then add up all the possible different possibilities and then try to get the most probable one.
Mm.
And that is like fundamentally the best you're ever going to do without having observed that much of the wave or the initial conditions of the wave.
Right.
And it gets even more complicated if you're inside a closed object, which like the ocean is not a closed object. It's essentially infinite, right? But now imagine you're just like in a swimming pool and that happens.
Hmm.
And it's even harder because like if you're in an open object and you can basically just kind of say like, well, the wave could have bounced off something, but there's not a lot of stuff in the ocean, so it seems unlikely. So, like, the most probable solution is that it just came from the direction it was coming in, and it just came from like, something happened far away,
Gotcha, gotcha.
and that's the most probable solution. Now, if I'm in a swimming pool
Like, well,
and
it could be anywhere. Could have
somebody
come from.
jumped in at the other side and the
Mhm.
waves sort of went out in a circular pattern and then they started bouncing off the edges of the pool and they all kind of like coincided on me in like very complicated patterns, especially if you like condense it all into like a smaller and smaller time. It gets harder and harder to construct the solution that is the most probable and
Mm.
maybe is impossible in some cases. So, and this may seem like a sort of annoying thought experiment, right? Like, who cares? But the reason you want to think about it when you're thinking about cosmology is because that is essentially what we're doing when we look at the Big Bang. Like, there was a thing, a really loud thing that happened a long time ago, and it happened and is still happening in every point in space for forever and
And
has
that's
always been
where
happening.
so are you talking about subatomic particles right now?
Kind of, but we're going to get into that in a second. But not even that, just empty space
Oh, okay. So you're saying
has
there's waves in the
noise
empty
in it.
space.
Has noise in it, and it has like a big anisotropic dipole in it, which means that there's like a direction to the wave and the noise, and that's the like if you look at the what's called the cosmic microwave background, just the CMB,
Mhm.
there when we look at it, like one side of it is red and one side of it is blue, and it's because that's a Doppler effect, and we are
Right.
moving with reference to the Big Bang, like we are moving.
That's crazy.
And it
We have
has the Doppler
velocity?
effect. We have a velocity. We can measure that velocity precisely because of the Doppler effect in the CMB, which is to say, like, with reference to the observable universe, our Earth is spinning at a certain velocity and our galaxy is spinning at a certain velocity, and then the galaxy is like drifting at a certain rate. And so you add up all those motions and you get something that is approximate to like what the Doppler effect is with the CMB. So
That's nuts.
that segues nicely into this concept of, well, what is space,
Right. So I learned
right?
something new. I didn't
Okay.
realize that space has a temperature. Like it's
Yeah.
sick or something. No. But like apparently 3 degrees Kelvin are of those people who also didn't realize. I assumed, I didn't think it was absolute zero, I guess. I knew that it probably wasn't that. But, I didn't know it had like a precise temperature. So if you go into the vacuum of space, it's 3 degrees Kelvin, which is still very, very cold.
Yeah.
But it's still interesting that it has some heat left over from the Big Bang.
Right. Well, and I think you just said like what is the most interesting part of this is like how do you define space? Like what do you think of as space?
Zero. No,
Yeah, no, go
I
ahead. Keep
mean,
going
I
with that.
guess I guess I've always thought of it as like, if I try to imagine it's just emptiness, right? It's just,
Yeah.
you know, the
It's the sort
void.
of lack of stuff, right? But that's actually a kind of weird definition, right? It's like a tautological definition. It's what isn't there.
Mhm.
It's not a thing
It's
you
like
can
trying to prove a
measure.
negative.
Yeah, exactly, and it's sort of infinitely regressive too. Like, well, what do we mean by 0? Like, how can you like,
Yeah,
how much harder and harder is it to get to 0 by, like, removing more and more stuff?
right.
And
But
is
wasn't
there
this is
actually
but this is one of the reasons that led Einstein to special relativity, right? Was because if you're trying to calculate gravity and you think of it as a force in the vacuum of space, forces can't act on each other if there's no medium. And so it's like that's how one of the things that led him to realize that gravity was actually the shape of space time, not
Yeah,
that there's a gravitational force actually acting upon us.
yeah.
So I still think of the vacuum of space. There's no medium. It's not like it's water, right?
Yes, that's correct.
Okay,
It's not a physical thing that can be, like, measured, and
right.
that's what's hard to think about it, right? And so it's actually helpful to go back to the thing I was talking about earlier in this podcast, which is this episode, I mean, which is you kinda have to, like, start constructing instead of it being a passive definition of what's not there, you have to start saying, like, "Here's all the things it couldn't be," and that's, like, a
Mm,
more formal and, like, easier definition to, like, work with. It's like, well, it's not
right.
matter, and it's not forces, and it's not whatever, and it's not and then, like and add up all those knots, and you start to get to a concept of, like, oh, space is a lot more complicated than just
Nothing.
passive sort of what we move through.
Interesting.
And that's important, and it's super important in relativity because then, yeah, you can imbue it with things like curvature
Hmm.
because it's all the things you when you go to take a measurement in a certain particular reference frame, it's all the things that don't happen that you would have expected it to happen. That's a feature of space. It's all like the negative features, and that's when we say space is curved, we're saying, like, you were supposed to go in a straight line and you didn't. So,
Right.
but when with reference to that,
But
that's
it's space time is curved, right? It's not just space. It's space
yeah,
and time.
but there's the 2 things are not like I try to talk about in the second chapter too, that, like, space is the freeze frame, which is not a real thing.
Not
It's
a
a
real
very the
thing. Gotcha.
instantaneous now is like a very not it's like kind of
Yeah. Well,
an
because also
illusion.
now doesn't, now is subjective, right?
Uh-huh.
There's a interesting truth of like if I was running and you were sitting still and we both looked up at the same star, we both would see the star. Like I would think I would see the stars from 3 days previous or something like that. Like the light would actually be different because of my acceleration versus you
Yeah, there's
standing still.
observer effects, yeah.
Yeah. Um, so it's an interesting way to realize that like now is dependent upon the observer.
Yes, the simultaneity is not
Hmm.
real, and it depends so much on the observer to within, like, very specific like, we got into some really cool stuff about, like, what light is at the end of the last podcast, and I think it comes back to that, like, time is, I think, a feature of how we measure light, actually, not
Yeah.
the other way around, but we don't need to get into that now. I think we can stick to the chapter. So we talk about space and it's helpful to think about, like, going from passive observation and the deterministic views to the sort of, like, constructor theories about, like, here, now I'm gonna, like, write down all the things I can think about that would describe a particular phenomenon and then add them all up, and then that's, like, just as real of a definition, and that's kind of more what how you have to think about space-time. And there's another interesting thing here, which is the horizon effects, right? So
Well, before we jump over to
yeah.
that, you talked about in the chapter if the universe were stuck in the exact center of two colliding whip cracks, would we know about
Mm.
it? It was an interesting thought experiment, but I didn't fully understand what you were trying to get with that. And then Andy did a fantastic drawing of it, which is really cool. But I was
Gives
like,
you, like, 2
what?
Indiana Jones,
It's like
like
what? So like,
yeah.
what are you trying to express with that?
Yeah, so I think the easier way to think about it is when, when we said, so we go back to the swimming pool,
Hmm.
y the sitting in a calm swimming pool seems like a more simple, like,
It'd be
thing to describe,
easy to
right?
figure out the
Easy to
probabilities
understand.
of the movement.
But if you keep going with the way that we solved the last problem, which is where did the wave come from?
Hmm.
And I'm gonna construct all the possible waves and all of the possible starting points, and then I'm gonna add up all the probabilities and, like, try to, like, minimize the
Oh, so it's like if
probability,
2 waves hit at the same time, they cancel
that
each
you
other
wouldn't
out, so you
measure
would never know
anything.
it.
And now
Gotcha.
suddenly that is, like, a perfectly reasonable solution to these sets
To
of
this stuff.
problems, and
Gotcha.
you start to be like, "Whoa, whoa, whoa, what if space is a lot more complicated than we think? Because it can just be, like,
Right.
these perfectly balanced opposing
Okay.
forces,
Okay, so
and
then you
that's just as
also
real of definition, yeah.
talk about it, and this is a really cool concept for me, is, like, what we're doing with, like, the, colliders, proton colliders,
The
or
particle
neutron
accelerators, yeah.
particle accelerators. It's kind of like trying to get our head up out of the wave just a little bit. That's how you
Mm,
described it in the book. So
yeah.
basically, we're by smashing these particles together, somehow we're able to observe things that normally would never be able to observe.
And okay, this is where it is nice to talk about the horizon effect, right? Because there are things you can observe at far distances that you're not able to observe when they're up
Up
close.
close.
And that's where you start to say, well, when have you ever seen a straight line in nature
Right, right. Yeah, they don't
that
really
wasn't like
exist.
constructed, like a naturally occurring straight line?
Yeah.
Because, and even the ones that are naturally occurring, like, or that are constructed, like, I'm looking at like the siding on my basement wall right here, like there's straight lines, but if I zoomed in really close, there's not a straight line there. There's paint, and it's all
Mhm.
jagged or whatever. Um, in the same way that we see straight lines or apparent straight lines in the wood, you see apparent straight lines on the horizon.
Mhm.
And when you look at things that are far away at time, which is very hard to understand, you can sort of see and observe things that you wouldn't otherwise be able to observe. And this is like kind of the interesting theory here, that like, or it's not even a theory. This is a fundamental part of physics and how it works. E equals mc squared was talking about how much energy is inside of a stable particle, like a stable
Mhm.
nucleus. And what the fundamental equations say is that, like, when you break apart a nucleus, like say you're doing a fission experiment, like you bombard and you hit like like a uranium atom or whatever,
Mhm.
and it breaks into two pieces. The mass that you add up of the two pieces will be less than the original mass.
Right, because the energy is, released as
That's
was
energy that's released, and that energy, like that mass
that
equals
mass
energy,
becomes
which
energy, yeah,
is, like,
and the
deeply
equation is
related
E
to
equals
light
mc
and how
squared.
light
Yeah.
propagates, yeah, and, like, that whole process is part of what we're doing when we, like, smash stuff together and we say, like, "Oh,
Mhm.
there's a weird little discrepancy there," like, at the horizon effect, but there it's like a force effect, right? But at the horizon of things that are very far away, and we have to just be careful and talk about what we mean by temporal horizons. I think spatial horizons are easy to understand because we see them and work with them all the time.
Mhm.
Temporal horizons, in the way that I'm using in the book, is to say, if you are moving very, very fast compared to something else,
And it looks like time
it
freezes.
looks slow, right? Sort of, kind of, except there are big things and there are small things. So the thing that is very slow that's happening at the Big Bang are these like slow echoes of a loud thing that happened. But when we smash particles apart, what we're doing is making them sound a little bit more like they did back at the beginning of the universe, and like when there were very high energies, and when
Right.
those high energies were sort of converting into particles, which is hopefully by now you're understanding like why this is so weird, and like the language is not quite right, but it's the best language we have because you're mixing and matching determinism, and you're mixing and matching probabilities, and you're mixing and matching like you know
Yeah,
forces
that
is
that
really a probability thing,
became
but yeah.
more I understood that better this time around, of how both determinism and probability are very useful in trying to understand these things, in the sense of, like, you have to figure it out probabilistically, but then that you can then turn around and use that to describe something deterministically. That's yeah, I'm,
Yeah.
understanding that better now. Although in this chapter you start calling the Big Bang, rather than referring to it as Big Bang, you keep calling it a crunch. Were you eating
Uh,
chips? What happened?
so that I had just read this book by Amadeo Balbi. He talks about it that way, and uh, he talks about the music of the Big Bang. He talks about the frequencies of it.
Oh yeah, that was a really cool part of this chapter too.
Yeah, I recommend that book, and it's like, and other ones that talk about that because there's like long, slow, deep frequencies that kind of sound like a crunch, which is
Hmm.
like a better way to. Now, but now they'll
Gotcha.
have crunch. They would have been a very high-pitched whine back in the day, back
Right,
in the
but now
beginning, but
because of
now they're,
the
like, spread out
Doppler effect.
because of this thing called inflation also, which is Alan Gust's thing.
So
That's
that's
another
what
one where I was saying,
got
like,
Biden.
"What?"
So that's what got Biden.
Inflation. Oh, yeah.
Inflation. Different kind of inflation. Although
Well,
you
and
do
well,
talk about space
yeah, I
as
was about
being
to
money,
say, maybe
right?
you tell me what you got out of the money analogy there.
Yeah, I didn't understand it. I even like highlighted it. I was like, why is it money? Um, you said space and time are like money, and I was like, no, I don't think so. Because space and time are like observable; they're outside of me, whereas money's made up. I guess money's observable too, and that's kind of a great way to think about it. So you're
Yeah,
saying
you can
time and
still
space are
observe people, like,
constructed?
exchanging it, right? You can
Yeah.
still observe.
It's interesting. Often had a fascination with money, not just because it's fun to spend, but it's also just like, it is interesting that so much of, our lives just center around something that we all just agree has value.
Mhm,
When in reality, it's literally just paper and ones and zeros inside bank accounts. Um, and it's really kind of good, goes to show how powerful, and this goes back to like Michel Foucault and, how people can
mhm.
give up their power to a system, and how the system can take on, literal life of its own. That always fascinated me. So I guess we're doing the
Yeah,
same thing
nice
with
nice
space and
deep cut
time.
in philosophy there.
Thanks.
Yeah, no, and I yes, it's this idea again, when you're on the inside of the wave, you have to start thinking about everything in terms of constructions,
Hmm.
and how can I like sort of construct a more complicated version of these descriptors that are interdependent and intersubjective is the term I start using.
In quantum mechanics, are they still using like Markov probabilities? Is that still what
Markov
they're using?
probabilities, yeah, no, they're very much important, but Markov probabilities just is a way of saying that everything, like every event, is independent from each
Dependent.
other. Yeah, independent. But yeah, anyway, so the money thing is this way of saying like, okay, but space and time are like a intersubjective phenomenon in many ways, especially if relativity is the way it is, and so that the intersubjective phenomenon, it's a quantity that we can all agree on because we're in a similar reference frame, but that it is not something that you would construct the same way if you're in a different reference frame. And so it was just a way of saying like, yeah, space is weird like that.
Gotcha.
And by extension, so is time.
So yeah, kind of goes back to because we're the observers, we're having a pretty big influence on the way that
The way we define it, yes. We're not having an influence on what's happening per
no, but the
se,
way that we
the way that
talk
we
about it.
understand it and talk about it,
Yeah,
yeah.
gotcha.
So, and then okay, so then there's this really cool part that I wanted to talk about and bring up, which is like when we look backwards and people like Stephen Hawking who actually thought really, really hard about how you map the forces in horizon effects, like in really, really things moving and we're inheriting from the Big Bang that we can see from the Big Bang. He showed that you have to have quantum indeterminacies to make the
Oh yeah, I
deterministic
googled that.
narrative work. What'd you get?
I don't remember what it meant now. It was one of those things where I read quantum into determinacy, and I was like, I don't know what that is. And I googled it, and I already forgot.
It's just exactly what we talked about last chapter, which is like you can't know where something was until you measure it.
Right, right, right. Yeah,
So, this is just a more formal, like, way of revisiting the claim that we already made, which is that like the deterministic view of the universe kind of breaks down, but not just that I can't seed it with enough observations. It's like, no, 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 there is no way to observe all the things that you would need to observe to make a clean narrative.
yeah.
And hopefully you're starting to see by now that I'm not just beating a dead horse for no reason. I'm not just like dancing around
Poor person.
like a bunch of random concepts for no reason. It's that like if we can be comfortable with the way that we are continuously tangling the hierarchy of the descriptors just to get through your everyday life, like just to understand how pools work in a way, like how waves work in a pool, or like how heat moves around when you're cooking, or like how whatever, then you can start to be comfortable with we also have to do it with the Big Bang. You
Right.
can't you can't think of it as an outside-in view. You have to think of it from the inside, that the narrative itself is gonna be necessarily incorrect because it cannot be written down consistently. It
Right.
fundamentally cannot be. And like Stephen Hawking showed that quantum indeterminacies are important for the equations to work. And then Alan Guth came up with this cool inflationary theory, which said, well, if there was little tiny quantum uncertainties in empty space at the moment of the Big Bang, and then the Big Bang expanded empty space really fast, then those like areas where we can't determine what was happening or where things had like sort of become a virtual particle that popped in and out of existence and then they got spread apart, that is enough to seed all the forces that you need to make atoms sort of start to happen and like that narrative happen. But it's very hard to understand because of this horizon effect. Like this temporal horizon effect where things are spread out and look very strange and weird and slow in one direction and very fast and hot and small in the other direction.
Oh,
Did
weird.
that make sense?
Yeah. So, yeah, that's the funny part about your book is that, and this is a very visual episode. It's great for an audio medium, but I'm going to show you a page of your book. I don't think you actually know how footnotes work. Half of this page is just footnotes. So the way Gavin used footnotes is he would put a footnote and then just continue the book at the bottom of the page for a couple sentences and then make you jump back up. So it's kind of like a jump around the page, you know? Because my understanding is the
Uh,
footnote is supposed to be you're citing something.
yeah.
None of these are citing anything. You're just explaining more stuff. But anyway, it does make it sort of like a choose your own adventure
Yeah.
style of reading.
I was doing a David Foster Wallace thing. I probably needed more editors at the end of the day. Tell me not to do stuff like that. But
I don't think the editor of this book read it, did she? That's
yeah.
probably mean to say.
I
She
had
might,
yeah,
maybe
no,
she
anyway, we
read
don't have
it.
to get into that. But no, I had several editors, but they did not rein in those silly impulses of mine.
Nah, I mean, it's fine. It is just kind of funny to be reading and then just like go down like, oh, there's a whole paragraph down here.
I should have just incorporated that into the text, by the way.
Yeah, and then you jump back up.
Yeah.
Yeah, again, I think this is some of the best art in the book too. I really love the giant chasm of unknowableness, no littering.
Well, why don't we do the thing? So last weekend, I went and recorded an album. And obviously, you can tell I think about this stuff all the time. So I wrote a song called Time. And
Woohoo!
I'm going to debut it. I think we're going to play it. Just Time is always waiting, contemplating what you gonna do. And I think I know the ending. Nothing too surprising, just a simple truth. Now I'm trying to catch a moment, I'm trying to take a photo before it slips away. And before it slips away. Time is always asking, demanding, what you gonna say? And I'm thinking about the ending. So many beginnings. What you gonna do? Are you bored?
No. You're bored. Oh, thank God, 5 seconds. No, that was really good. That's cute.
All right.
I will say, Gavin, your music is always lands on the side of like a little sad. Your very first album had a couple of songs on it that were, exploring some of the traumatic experiences or traumatic events that had happened in our
Sure.
family's life, and so that one always got me to tear up. But this is a very good song. Now, what does it mean?
Thank you. It is me musing about time, but from like a personal perspective. About
Time's
time
never
is always
demanded
there.
anything of me.
It's always music. It hasn't really. You've never felt pressured
Oh, that's what you're talking
by the
about. That
passage
makes
of
sense.
time.
It's never actually talked to me.
Yeah, well, that's what's cool about the format. Time is whatever. Love is whatever.
Yeah, whatever.
Time is no. I mean, like in the metaphor. Like it's like
Yeah,
time is
gotcha.
X. But anyway, no.
Yeah. Well, that's
it's
exciting. Are you
Yeah.
gonna? So you just recorded, so it'll be a
Yeah,
little bit
this
before
is a sneak
you.
peek.
Before your songs will be up on Spotify. But once it is, we'll link it down below.
Absolutely, we'll link it, and then if you
Um,
want, I need to like come up with something. But
The other day I was Gavin's old band, The Shape of the Earth. This will not be The Shape of the Earth. Will be Gavin's solo
under
project.
my name, yeah, Gavin Bascom.
Gavin Solo.
No, just Gavin Bascom.
He wants to be like Han Solo. But yeah, I was on The Shape of the Earth the other day. I periodically go over there and give a few songs a listen. Want to be a rock star. But
Oh, you mean like you were on Spotify listening to it?
yeah, and it surprised me. No offense, but it said you had 2,000 monthly listeners. And I was like, wow,
No, people
that's
still
pretty
listen to it.
cool. People still listen to your stuff. That's
Yeah.
awesome. And you have
No,
30
we have
songs
listeners
out.
in every continent and in 300 or 400 countries, and
You guys still paying for clicks in India? Just kidding.
never did that. Never did that a single time.
Yeah. No, if Valente will ever listen to this, but if he does, I remember years ago, Tim made a joke and I didn't get it. I was asking Valente, how successful his music was, and Tim was like, "Oh, he's got like a really big following in India." And the joke was that he paid for clicks.
Pay for the clicks.
And I, for a long time, would repeat to people, "Yeah, he's got a following in India."
Oh, not cool.
That was not a joke.
Not cool. You didn't get the joke. You thought it was real.
So sorry about that, Valente.
Well, things like that do happen though. I mean, it's
Yeah, they do. There was
my
like that
friend's
one guy
band like
from
got
South
weirdly
Africa, right?
big in Japan, and then they like sold a bunch of records there, and they were gonna go on tour there. It was just like a weird little punk band thing that I don't know. Anyway, yeah. So I'm just excited because it's like fun. Obviously, I don't know. These topics mean a lot to me, and I think we've spent a lot of time thinking about them. And So I made onto this record, and this was a nice way to just let people know I'm going to put out a new record, and I'm really happy with all the songs, and they're not all sad, I promise. Some of
All right,
them are,
are we done
but
plugging your stuff already? Get back to space.
sure, if you're so
Jeez.
eager,
No, I'm just kidding.
go ahead. Tell me, what do you want to talk about next?
Spinners. So Gavin just casually drops this incredibly complex physics math issue in his book. He's like, yeah, that's just like spinners and da da da. And so
Yeah.
I'm like, I don't know what that is. And so I went down a hour-long rabbit hole of trying to understand, ended up at some mathematician's blog. I had to figure out what Euclidean versus non-Euclidean and Markowski physics. I don't know. It was a lot. So you explain to me, Gavin,
Do
what is a
you
spinner?
I have a question for you first. Do you
Yeah.
think that you are better off as a human now having gone down that rabbit hole, or do you
I
wish you hadn't done it?
mean, no, I'm embarrassed to say I think gave up before actually understanding it. I just got frustrated and was like, is there no one out here who can just explain to me in plain English what a spinner is? And the truth is there was one kid on YouTube that had an interesting
Yeah,
experiment
YouTube
where
is
he
a good
held he
research for
held
this.
a water bottle, but he was specifically just talking about how there's an interesting thing about a spinner is that when it does a 360 degrees, it's actually facing backwards. You have to go
That's it.
720 degrees for it to spin
Yep,
around.
yep.
I guess that's a unique thing to a spinner. I don't even know what it is though.
Let's back up. Let's back up. Okay, because we're getting too much of it. So first of all, I want to just push back a
Is it a particle?
tiny little bit. A spinner is technically an operation. Okay,
Ah,
mathematical operation. But
like the little one
what
that
I
goes
did
buzz.
not do was just drop a heady concept.
Fair
I
enough.
actually spent a lot of time trying to figure out how much or whether or not to talk about this at all.
Right.
And I think that I gave you just enough that if you're interested and you want to go down rabbit holes, you should go down rabbit holes. I also didn't like preach it or proselytize it because it's just kind of like one of the better ways to think about what is hard about the math at
Mm-hmm.
these sort of weird temporal horizons that you have to operate at.
Okay.
And yeah, and you're right. I could have had better like introduction of the concepts for sure. But
So
I didn't like go too deep or too little. I think I hit that pretty nicely. But let me just back up. Okay, so the analogy we use, the thing to think about is the imaginary number. Okay,
hmm
which if you're not comfortable with imaginary number, you could use 0 or you could use negative numbers. It doesn't matter. It's just back in the early days, in the same way that we used to not be able to draw perspective in pictures because we didn't have a concept for how to visualize it, which maybe means that people just didn't see it and just didn't understand their vanishing points on the horizon, or maybe they did, they just weren't able to like write it down.
hmm
Like obviously it existed, but like how prevalent was it in people's minds? It's hard to say because nobody knew how to like catalog it.
This is like the whole thing where like the color blue wasn't
Yeah,
described
yeah, yeah,
until
yeah.
like the
In the Odyssey or
1500s or
whatever.
something. Yeah.
Yeah. So it's hard to say, but like when mathematics evolves and like a really clever thing happens, then it becomes a new semiotic like point around which people can now operate and do things they couldn't do before. And like the concept of 0 is one of those. Like a mathematical concept of 0 that comes before 1 was an invention that took a long time to take root. And the same thing with negative numbers. There's no such actual thing as a negative apple, right?
Right.
You can have one apple. I can do one apple. I can do two apples. I can't have negative two apples. That doesn't actually exist, but it's an intersubjective thing. Just like money, we
Yeah.
agree negative two apples means that if I ever have two apples, you have to give them to me, or whatever. Some version of the whatever in the context that means. It's the opposite of the
Yeah.
two.
And so an imaginary number is where there's no actual number that you can square and get -1. And so you
Right.
imagine that there is a number. And so that's the basis of imaginary numbers. I got that from my
Yeah.
Googling.
Yeah. And you just brazenly say, okay, this is how this works now. We are just going to agree that this is how it works, and
That,
then just move on.
yeah.
If you do the same thing, and this is where, again, you don't need to know where it came from, you don't need a why, and you don't need to, like, go to the University of Colorado Mines or whatever to, like, learn this stuff, which they teach it there really well. But, um, e the basic concept is there's an operation, a mathematical operation, the same way that, like, adding and subtraction is a mathematical operation, but you can do an operation that says, if I have a vector that's pointing in a certain direction when I start. I apply this operation, and it has simultaneously rotated and translated.
Okay.
It didn't rotate and then translate.
It
It
rotated
did both at
both at
the
the
same
same time.
time, which is not physically possible. It's
Gotcha.
not actually physically possible, but we're just going to assume that we could make something up that does that operation.
Right. And so that was, yeah, I did listen to that same mathematician where I got reading his blog. I watched him on an interview and he was talking about how when you measure like an electron, for instance, you would get two complex numbers at the same time
Yeah.
when you would think you would get one complex number. And he goes, that's essentially where spinors come out of, is like what you're saying. Is basically there's two things happening when really only one thing should be happening.
Should be happening, but there's actually
Yeah.
two things happening.
Two things
And
happening.
we can't figure out why or how or whatever. In the way it's not like, again, I'm really happy that we've done the podcast because now we have some language to talk about it.
Right.
In the same way that before the podcast started, you may have thought like, the universe is fundamentally deterministic and probability is just a way to describe deterministic stuff. Then after chapter 2, you might have said, well, wait, no, the universe is fundamentally probabilistic. And determinism is just a trick that we use to like describe all the probabilities moving around.
That
Hopefully
is
by
what
chapter th-
happened.
hopefully by chapter 3 you're seeing I don't know what the hell is happening. There's probabilities everywhere and there's determinism everywhere and you can like keep going back and forth like cuz now I'm inside the wave and I have to go backwards and I have to like try to come up with all the deterministic waves and then do the probability of the deterministic waves. Like the mathematics is so semiotically promiscuous that you can
Mm.
apply anything to anything regardless of the
There's those
hierarchical nature of where it
sexy
came
words
from.
again.
Yes. The spinners are like the deepest like the deepest sort of expression of this,
Gotcha.
which is that at the most deepest level of what we can measure about how particles move around, in order to get all the forces to like work and operate with each
They're
other,
doing
our
something impossible.
best guess is that you have to do something that is physically, literally physically impossible. And if it is impossible with a symmetry of a half,
I'm
it looks
starting to
like
think we know less than I thought. Um,
yeah, I love that. I love
well,
that. That is
so,
why
okay.
I wrote the book,
But
just so people
that
could
was
have that moment.
just like, wait a minute, they don't know what they're talking about.
Nobody knows what they're talking about.
Well, it was interesting. This I actually need to figure out his name. This blog that I was reading, I think it was Peter White. Uh, he was at a university. He very much was in his blog was getting very angry that people are still dedicating a lot of time and effort to supersymmetry. He's like, no,
Mm,
we proved it. It's dumb. Stop talking
mm.
about it. It's a failed thought experiment. It's a failed theory. We should no longer be giving any, research dollars to it and people shouldn't be doing lectures on it. He's pretty adamant about that, which I didn't actually realize. I thought that it was still possible that supersymmetry could be out there, but according to him anyway, he thinks it's completely disproven.
Well, there's a lot of flavors of these different things. So, like, I think the standard model is still that was like one flavor of the standard model, right?
Right.
Supersymmetry. So the standard model is still alive and kicking. Um, string theory, I think, is I
Yeah.
don't know. I
He
think it's
also
getting
said
less
string
and
theory
less.
is dead. He
Yeah,
said supersymmetry is dead.
yeah.
He is of the many worlds. And then also,
Mm,
he talked a lot about how I guess there's a theory made by Penrose, the
yeah,
twister space.
yeah.
I don't know
Penrose is an
what that
interesting
is,
guy. Yeah.
but apparently he came up with a model of 4D space that explains twisters, but not, or explains spinners really well in the Euclidean framework,
Oh, right.
not very
But not
well
in the
in it,
non-Euclidean.
and no, in the Minkowski.
Minkowski. Yeah.
Minkowski. So basically, when you yeah, when you throw special relativity in the mix, suddenly spinners become they don't make any sense again.
Well, first of all, I want to point out that you did retain a lot of stuff from your rabbit hole deep dive,
Fair
obviously.
enough. Fair enough.
So, but the second is, yeah. So this is sort of a classic thing. So spinners are a way, they're like a way for quantum field theory to help do special relativity and gravity because the symmetry spin 2 is the graviton and it works, but it doesn't work in a non-Euclidean geometry, which is your general relativity should extend to non-Euclidean space-time as well. Anyway, this is already way further down than we needed to go. Like, I'm telling you,
Gotcha.
like,
Yeah.
for people to understand and appreciate the beauty of the strangeness of it, you do not need to understand spinors. You do not need to understand, like, how to do the math and operate it and, like,
Yeah.
all the point I was just trying to make, and I think this is plenty. Obviously, if you want to go deeper by all means, but I'm just saying you don't have to if it's scaring people off. Like, the cool and beautiful thing about it is that there is fundamental unknowableness. There's a chasm of fundamental unknowableness at the horizons, which is not that hard to grasp. Like, of course, we don't know what's happening at
It's
things
too
that are
far
either
away.
far away, they're really far away, they're really far away in space, or really far away in time. Those are things. But what's weird and hard to grasp is that, like, the atoms that make us up, we can only measure them in ways that are far away in time. And that's why you have to use this weird mathematics. And part of that is because it's high energy, but part of it is because they are swirling forces that sort of started swirling at the beginning of the Big Bang. And so there are things happening deterministically inside those forces that started at the Big Bang and haven't finished yet.
Yeah,
They're
that's the
still going. They're still kicking. That's why they're atoms.
the Big Bang is happening now.
Everywhere. Inside the
Everywhere.
atoms, inside the empty space, inside the
You should,
whole thing.
should get that
That's a
tattooed.
yeah. That would be a cool one. I actually have thought many times that if I got a tattoo, it would be something from the book. Like, it would be like the marble or whatever, but I haven't
Yeah.
actually done it yet.
It would hurt. Stick needles in your body. Oh. Whoa.
Fair enough. So we end the chapter with
Big gulps.
no, I want to actually read I want to read a paragraph I'm very proud of. Okay. So we're talking about going from, like, describing unknowables and fundamental constituents and mapping them to the fundamental subatomic particles, but then, of course, they're not actually particles. They're a fancy set of engineered bookkeepers telling us what is impossible to trace directly backwards in narrative determinism. What we'll see as we move forward, however, is that the particles' features themselves are not actually impossible. They just aren't palpable in the sense that horizons aren't palpable. They're observable and important to observe, but not real in any way that local classical terms are real. What's more, the shift in thinking is nothing less than seismic. It corresponds to one of the most dramatic shifts in modern thinking that we've ever witnessed. It represents a massive upending of the traditional model of the universe, where everything is caused backwards in time to forwards in time tidiness, but instead, noting that there are unobservables affecting things simultaneously across multiple timescales, and this should be upending the previous reductive models of how things work. Maybe I shouldn't read from the book anymore, but
I was gonna say, sorry, you lost me. I was daydreaming there.
yeah, I need a new
What?
version maybe, but
There's
no,
Chat
it
GPT.
is seismic. It is a huge seismic shift in understanding, and it's about going from outside the marble to inside the marble,
Hmm.
and, like,
Yeah,
that
yeah,
is what
yeah.
is super exciting to me.
We're inside the wave.
We are inside the wave, yes. The
That's
big,
pretty
giant,
cool.
loud, weird clap that happened.
It's clappy, it's crunchy, it's bangy.
Yeah,
It's all the things.
it defies all
I did like
descriptors.
I think I will check out that book you referenced a couple of times,
The
about talking about the Big Bang being a
music of the Big
musical.
Bang, yeah.
That'd be pretty cool. I can't listen to the music of the Big Bang. Should drop another
Yeah.
album. Woo, woo.
Yeah, that's what I said. No, the album's gonna be called "Time Is Always," not the
Time
music
is
of the Big Bang,
always.
because that would be
Nice.
confusing.
Yeah, if time isn't always, though, it'll end. It starts and it ends. No, I had the random thought equation, not equation, not an equation, thought experiment for you. Help me out with this one. If I got in a spaceship and I traveled almost near the speed of light for a really long time, like say I somehow was able to survive because I'm a clone or something, and I can make it to another galaxy, and then I stopped, I looked around at my observable universe, it'd be different, right?
Yes, so time for you slows down and it speeds up for in the reference. That's remember the movie Gravity when they, like, go close to a black hole
Yeah,
and then everybody's old? It would be
yeah,
something similar to that, like, if you go really fast versus
right.
so
Interstellar was an
you
interesting
haven't
movie.
aged, but everybody else has aged.
One thing I will give Interstellar, they did a black hole justice. Not the whole going inside of it, that was silly, but
You
the
know,
actual
yeah,
picture, the
yeah.
visual
That
was
was that,
awesomely
like
accurate.
yeah, it was accurate, and it was based on a bunch of, like, really cool simulations, not unlike the kinds of simulations that I do in
Well,
my work,
yeah, what's cool
and
though is that that was before we had actually gotten an image of a black hole. And now after that movie came out, we actually now have an image of a black hole and you can look at it and it's like, oh, yeah, they did a
see the
really good
features.
job.
Yeah, yeah,
I mean,
and
obviously
they
the Interstellar
popularized
looks
that, which
cooler.
is really, really cool, and I think,
Yeah.
that was one of the first movies that,
I didn't like the
did
AIs and that
or
stupid,
is it
weird
they did
robots.
time travel right, and I don't know about, like, going back to visit your, like, daughter's, like, clock or whatever, but the at least, like, the time travel
They
that
did
happened
time
in it.
dilation, right? They didn't do time travel
No,
correctly
they
because
did
that's
because he
nonsense. You
went in
can't
the
do
he
time
went in the
travel.
black hole, which I know it's not true, but he went in the black hole and he, like, talked to his daughter. I was saying in the situation where you can do time travel, it will always have happened.
Oh, right,
They're
right,
they're
right,
the ones that
right.
did that right. Like, it's like the looper
Sure.
version. It's not
The
like
looper
the or
version,
sorry,
yeah.
non-looper version or, like, not
Non-looper
Back to the
version.
Future version where you can, like, come up with
Go
all these
back and change
paradoxes.
stuff. Yeah.
Yeah, because this is not how it
Yeah.
would work
Yeah.
in my mind,
But
but
time travel is impossible. Brian Cox told me so.
yeah, I tend to agree with that. But I also don't think multi-worlds are real, and
I
I
don't
think
either.
that's
We'll have to
all
get into
yeah.
that because the math does suggest it, but I don't think that I don't know. It doesn't make sense to me.
Here's
My intuition
now we
tells me
have
no.
now we have a framework to talk about it. I don't think it makes sense from the inside out. I think it makes sense
Hmm.
from the outside in. And I
That's
think
a
that
good way
all
to
the outside
describe
in
it.
theories are just wrong. I reject them all
Mm.
because I just think they're wrong. I don't think they're seeing the whole picture.
Yeah. From a cosmological perspective, I think multiverse is very probably true. I don't think that from the quantum, like we've talked about, that because of the different quantum states and the fact that when you measure it, the waves collapse, I don't think that necessitates meaning like that was a branch in the universe and now there's another universe where we didn't measure and the wave didn't collapse. And that's when you get into the whole Schrodinger's cat thing where it's,
Yeah.
is there two universes, one where you open the box and the cat's dead, and when you open the box, the cat's alive? I don't think that's true. Although
See,
there's physicists right now who, will argue, no, it is like there is multiple
that
universes
is true.
splitting.
You're right. There's people that argue everything. But I'm not trying to denigrate anybody, but
Well,
like
I would
it's
say that the math doesn't, it doesn't say it has to be that way. I think it says it could be
it
that
is
way
an
to some
interpretation of
people.
math for
Yeah.
sure. But I will go back to the original Schrodinger, like, his intentions were not to convince you that there are
No, yeah,
such things as
the
alive
opposite.
cats and dead cats. It was to make you, think, like, what's that you don't understand about the theory. Because here's the thing, you will
I thought he
never
was
the
trying to say
theory
that the theory was wrong. He was trying to say like we haven't figured it out yet because this can't be true. It's kind of his point.
yeah, I mean, we could go back and read specifically at what point in his career he was saying what, but, like,
Yeah.
and I'm sure it changed, but, like, you will never, ever, 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 ever witness an alive and dead cat.
Yeah.
That is not how it works. You will never
Can't.
open the box and see it, and you can never, ever assume that it is both because it is
Right.
not. It is either one or the other. It's
Yeah.
just that you can't predict what it's gonna be until you open it.
Right.
And there are weird things about how if you, like, were somehow able to get 2 cats and, like, and have the particle that kills them be intertwined, then you could tell whether the other one was alive or dead. But again, you will never, ever, ever in the
That's
history
the
of
quantum
universe
entanglement, right?
you will never in the history of the universe see an alive and dead cat. There's nothing in the math that says that it exists.
I mean, I can get two
So
cats and kill one cat.
but not the same one. It won't
Oh,
be
that's true. It won't be the same. Like, gotta be
the
specific with your
causal
language.
determinism thing does hold true. Like, even though quantum mechanics says you can't force it to be one thing or the other, it still is true. Like,
Yeah.
you still determine things by interacting with them.
Yeah.
Um,
Yeah.
I don't know. Yeah, it's all fascinating.
Again, this brings me back to the end of that TV show called Devs, where the kid jumps off the cliff because in his mind, one universe he'll float to the bottom and not die, and that'll be that'll like all the other universes he'll die, that he won't exist in those anymore.
Yeah, he knows he'll just
His perspective will be the one that
yeah.
survives, but then he dies because he
Well, in
was
all the other
wrong.
universes, that's why it's so selfish. Because in all the other
Yeah,
universes where you die, the people that were with you have to be like, oh,
he did.
okay,
But so what I'm saying is, don't go jump off a cliff to see
please don't do
if you float down to the bottom.
that.
So I don't think you will.
Yeah, Chris Agats did a great video on this.
Yeah, they do
Yeah.
good stuff. Good stuff. All right. Well, I guess we can cut it off there. Big gulps, huh? See you next time.
Well, see you next time.
Chapter 4.
Yeah,
Almost
we're
done with
gonna
this
get
book.
to it.
Jeez. That's it for today's journey through wave functions, the nature of space, and the strange math that makes the quantum world tick. Thanks so much for listening to I'm Finally Reading My Brother's Book. If you enjoyed this episode, please follow the podcast, leave a review, and share with a friend who loves big questions. In our next episode, we'll keep pushing further into Gavin's book and explore how these concepts connect to a bigger picture of the universe. Until then, keep wondering, and we'll see you next time.